Hello, everybody. Welcome back to the I Heart Pluto Science Speakers Series. My name is Amanda Bosh. I'm a planetary scientist at Lowell Observatory and also the Chief Operating Officer. I've spent a good portion of my career studying Pluto, and tonight it's kind of a treat because we're going to be going back in time to look at the first time that Pluto was identified as a new planet back in 1930. That's the overarching goal of this whole festival, the I Heart Pluto Festival, to celebrate the 92nd anniversary of the discovery of Pluto. And it's also the literal definition of our theme, Worlds Discovered, because in 1930, Clyde Tombaugh discovered a new world here at Lowell Observatory in Flagstaff, Arizona. Before I introduce you to tonight's speakers, I wanted to just give you a little bit of information. I wanted to tell you that you can find more information about the I Heart Pluto Festival by visiting our website, iheartpluto.org. We have events going on every day and night through Monday, February 21st. So come and join us. I'd also like to thank the Northern Arizona DX Association for sponsoring tonight's science talk. Our speakers tonight, and we have three of them, they're all on the staff of Lowell Observatory and therefore are my colleagues. Brian Skiff is an observer, a research assistant, and basically just a font of astronomical knowledge. He's been integral to the LONIOS Near-Earth Objects Survey and was the person who took the final glass plates with the Pluto telescope before it was retired to its current home here on Mars Hill. Lauren Amundson is our archivist and librarian. She and her staff work to collect, preserve, and provide access to the observatory's historical artifacts, which is really quite a daunting task because there's a lot of them. And Stephen Levine is an astronomer and also the Lowell Discovery Telescope scientist. His research interests are in large astrometric surveys and the dynamics of astrophysical disk systems. He's also the principal investigator of a project to preserve some of the information on some of these old plates, which we'll be learning about tonight. Tonight's live stream is a little different from our other programs, if you've seen some of them. In that we're going to show you 3 pre-recorded videos, and then we'll stop between each of them to chat more with our speakers about some of the topics that have been brought up in those videos. We're doing this because we really wanted to take you into the archives to see some of these historical artifacts, and this was the easiest way to do it. So, we're going to get started with tonight's program, History Captured on Glass. I want to just preface this by saying that for about 10 years, I led a program through the Massachusetts Institute of Technology where I would bring a group of students, undergraduate students, to Lowell Observatory each year to learn about the science that was being done by the astronomers here. One of the highlights of this visit every year was when Brian Skiff would lead us all on a tour of the plate vault and show us the actual Pluto discovery plates. It was really a thrill to get to see them and to find out about about all of the circumstances of the discovery. And so tonight we hope to share some of that with you, with a larger audience. So with that, we're going to get started with our first video.
So I'm Brian Skiff. I'm a research assistant at Lowell Observatory, and I've worked here for a long time. And I guess my qualification for talking today about the discovery of Pluto is that I was the last regular user of the Pluto discovery camera, the telescope that was used to take the plates to discover Pluto. And I also knew Clyde Tombaugh. Got to talk with him on several occasions about using the camera and also about the discovery of Pluto. So I thought I'd tell, really the story of the discovery of Pluto has to begin with the discovery of Uranus, which happened in 1781. It was found by William Herschel completely by chance. He was using about a 6-inch telescope that he had made, a reflecting telescope that he had made. And he was engaged in a survey to just sweep the sky to look to see what was out there, simply because it hadn't been done by the time of Mozart and Haydn in the late 18th century. And amongst the things he found was one night was a slightly object that was slightly bigger than a star, a dot, rather than a star or a comet. He discovered comets, but it wasn't fuzzy like a comet. And he recognized it right away that this was something that was not the usual thing. And so it wasn't clear, actually, for a couple of months that this was actually a new planet out in the outer part of the solar system. So the presumption was that there must be another large body out beyond Uranus that was causing this perturbation. And several people worked on this problem, and notably Urbain Le Verrier in France and John Adams in England, and who were both mathematicians, not really observing kind of astronomers, calculating sorts of astronomers. And they both came up with more or less the same answer at more or less the same time in 1845 and 1846. Johann Galle and Heinrich de Rest, who were two observers, used an 11-inch refractor that was a fairly large telescope at that time to go and hunt near the predicted location that Le Verrier had announced. And they had, much to their advantage, a new set of charts that had not been published, a new set of star charts that included a lot of faint stars that were not otherwise cataloged. And so that had just been printed in Berlin. And so they went out one night, looked in the region that Le Verrier had announced, and with some scanning along and identifying each star one by one. And it took them about 45 minutes to come across the extra star that wasn't on their charts, and that was the planet Neptune. By the end of the 19th century, it seemed as though that neither Uranus nor Neptune was going in quite the right path. And people thought, oh, there's another big planet like Uranus and Neptune, what we now call an ice giant planet, out beyond those guys. There's another one out there. And so several people took up this task, including Percival Lowell, who in the first years of the 20th century started doing these calculations to hunt for planet X, as he called it. Other people had different letters for this unknown body. And he did work himself, but also employed computers, people who did computing, to carry on these calculations. And in 1915, not too long before he died, published a large tome it was called A Memoir on a Trans-Neptunian Planet, that showed from his calculations and on the basis of the data what seemed to be perturbations of Uranus and Neptune, that where this body was, this fairly large body, and he gave, as Le Verrier and Adams did, gave two positions 180 degrees apart on the sky, so halfway around the sky, where this thing could be and cause this perturbation. Lowell died in 1916, and things came to a halt, and there was a hiatus for basically 15 years. There were two searches done during Lowell's lifetime to hunt for this planet X. One starting about 1905, and then another one in the early teens of the 1900s with a 5-inch camera, and then later with the second search was done with a 9-inch camera, a 9-inch aperture camera. So fairly good-sized astrographic kind of lens. And those were both unsuccessful, mainly because of the way that they tried to examine the photographs. They didn't have, Lowell or the other folks did not have a way to examine the plates carefully to look for a moving target amongst the fixed stars. So in 1929, the Pluto camera, it was called the 13-inch astrograph lens at the time, was set up, and there's a big long story, of course, Clyde Tombaugh being hired as this young fellow to come and basically do the observing, to take the photographs. And during the dark time, when near new moon, he would take plates, stash them, process them and stash them away. And then during full moon time, when he couldn't take the photographs, he would spend, or when the weather was cloudy, he would do the blinking, which was a very slow, and it's still a slow process. In the spring of '29, Tombaugh started observing, and they were just kind of taking plates. And then there was a break during the monsoon season in the summer. And amongst the things Tombaugh did was to read Lowell's memoir on the trans-Neptunian planet. And that told him right away that he needed to take the photographs only right at the opposition point in the sky, the place directly opposite the sun. So the Discovery plates ended up being taken at the end of January in 1930. And again, it was the dark time. And then a couple of weeks later, he got around to actually doing the blinking of these plates. And one of the plates he took at the end of January was centered on the star Delta Geminorum in the constellation Gemini. And he knew from having read Lowell's memoir that was the area where one of the locations that Lowell predicted that the planet X should lie somewhere in there. And so in the middle of February of 1930, he started this process of blinking. So he got halfway down, in fact, not too far from Delta Geminorum, and saw this object moving. And he told me he saw right away that this was it. He nevertheless had to, do proper duty and make sure of what he was seeing. So along with on the Discovery plate jacket, there is an account that he wrote in June of 1930. That's the oldest thing we have of in his writing specifically of what actually transpired. And so he says, examination of this pair of plates began about February 15th, but I could devote only part of the time to the blinking. The thickness of stars slowed up the work considerably because it was in the Milky Way. So on February 18th, so 3 days later, at 4 p.m., Planet X was discovered using the blink comparator. The following 3/4 of an hour was spent investigating the amount or shift of apparent motion of Pluto, and no comets, and Planet X Pluto found at last.
That was a really fascinating story about the discovery. I'm wondering, Brian, if you could maybe say a little bit about how Clyde Tombaugh knew that it was Pluto when he discovered this moving object.
That's actually a great question, and it was something that he basically told me and that I read about as well. And when he started observing in the spring of 1929, they just started taking photographs and really didn't know quite what they were going to be doing or with them or how they were going to actually identify the object. And but it was useful, obviously, for him to get used to simply running the telescope and what could be done with it. And so during the summer monsoon break, when most of the nights were cloudy, Clyde actually went through and read this memoir of the trans-Neptunian planet that we showed, and realized that basically the only way for him to actually identify the object unambiguously was to take the plates right at the opposition point in the sky, directly opposite the sun, sort of the midnight sky. And the reason for that is that most of the motion for objects out in the outer part of the solar system, most of the motion that you see from night to night is the result of the Earth's motion going around the sun much faster than those outer bodies that are going more slowly. And so he saw that, if he just had the pictures taken a couple of days apart, that anything at, say, 40 times the distance of the Earth from the sun would be moving, X millimeters on the plate. So he had a rough idea of how fast these objects were going to be going. And so he progressed through the autumn and winter, taking those plates and doing exactly that. And so when he got around to actually blinking this Discovery pair that were taken in late January of 1930, a few weeks later, he was able to start doing the blinking to examine the plates. He saw this quite faint object, much fainter than they were expecting, moving with exactly the motion that they were expecting. And he told me, he said, as soon as he saw it, I knew this is it. And just because of this motion, even though he, of course, had to do all the due diligence to check on extra plates and make the measurements and so on to convince himself that this thing was actually out at the distance that Percival Lowell had predicted.
So because the motion between the two plates was of the right order of magnitude. So that's how he knew it was something in the outer solar system and not an asteroid.
Couldn't be an asteroid, for instance. And even his exposures were about an hour long. And so the ordinary asteroids that are between Mars and Jupiter actually show up as a trail about the length, in fact, of the spacing of the two images of Pluto. And so
and of course,
he knew those were easy to spot because they were trailed. Right. But anything, very distant, Pluto did itself, or Planet X, as he would have referred to it at the time, didn't move during the 1 hour exposures at the image scale of the plates.
And of course, we didn't know about any of the Kuiper Belt objects or tuning objects because they're much fainter.
Yeah, I mean, when the first of those smaller bodies was discovered, it was actually bright enough that I decided to go and look on plates to try to find it once there was an orbit published for that. And it was, that object was actually visible, but only just barely. It would have been something that anybody blinking the plates would have missed.
Oh, this was QB1. So
QB1.
You were looking in the old plates. So okay.
So it actually shows up at just barely.
Just at the limit of the plate.
Yeah, right at the threshold, just barely above the grain noise of the photographic plates.
Oh, wow. Do you know if there were any other objects discovered on this particular plate, the Pluto Discovery plate, besides Pluto itself?
Oh yes, on the original plate jacket, he indicates that there were no comets that he found. He was hunting for comets too, but I think the plate jacket says that there were 8 asteroids that he had marked on the plates. So there were a number of asteroids, which is one reason we would like to scan the plates digitally so that we could actually measure those much more readily than we were able to in the past.
And of course, most of the asteroids are
certainly now all of the asteroids bright enough to show up on the early plates, particularly, are now known, and so we can predict their positions pretty accurately.
Right. Most of the asteroids are in the main belt of the main asteroid belt, which is between Mars and Jupiter.
Mostly. There are a few near-Earth objects. In fact, when Ted Bohl and I, 20 years ago now, were actually trying to identify old archival observations of near-Earth objects, we actually found pre-discovery observations of Apollo, which is one of the earliest known near-Earth asteroids. It was where Tombaugh had actually marked the object about a year before it was discovered.
Oh, wow.
So there may be a few surprises on these plates. There
may be, absolutely. Yeah. We actually have a question from our audience. I'll just bring this up here. Why did they think Pluto? From Cody, why did they think Pluto was so large?
That's a good question, and the reason is simply that there had been these, relatively large, the ice giant planets discovered in the case of Uranus and Neptune, and it seemed, as I say in the presentation, it seemed as though that both Uranus and Neptune were getting perturbed by yet another large body out beyond them. And we now know that, that happened, we now know because there were systematic errors in measurements of the coordinates, the positions on the sky of Uranus and Neptune, that everyone, including Lowell, but other folks as well, thought were the best observations. And so they used those to try to determine the size and location of this large body. But it turned out that there was actually systematic errors in those data, which we only know now because it was only identified that was the case in the 1970s. Once the orbit of Pluto itself was small enough and you could see the residuals and the positions, the errors in the positions that were published back a little bit before the turn of the century. And so everybody thought that there was this big object out there, but it turns out that, of course, we now know very well that Pluto is so small that Uranus and Neptune don't even know that it's there, except a very large number of decimals in terms of the gravitational effect on those very large planets that are bigger than Earth.
Thanks. Great. We're going to move back now to the second video in our series. So we will come back and talk to you again a little bit after we all watch that video together. So see you all soon.
Hi, I'm Stephen Levine. I'm an astronomer here on the staff at Lowell Observatory, and I'm also the telescope scientist for the Lowell Discovery Telescope. So one of the appealing aspects for an astronomer coming to Lowell is that Lowell has a roughly 100-year collection of astronomical photographs of the sky, various objects, various portions, and a big piece, especially today, of astronomy, study of objects over extended periods of time. The digital age only really goes back to the late 1970s, 1980s, but if we can somehow make use of photographs taken as far back as the early 1900s, we can extend the time baseline that we can use to study objects by a good 60, 80, maybe even as much as 100 years. And one of the things we've learned is that A, we never know what we're going to find when we suddenly expand our study period, but also that the longer the period we have to study, we almost always find new phenomena in objects that we didn't expect. Variable stars show periods of variation that are almost always as essentially correlated with how long your study period is. If you studied for 10 years, you find 5-year variations. If you study for 40 years, suddenly you find these additional variations over periods of 20 or 30 years that you had no way to expect. And so I'm looking at this as not only are we interested in taking new data, but we have this gold mine sitting in our basement of data that are, until they are digitized, are difficult, if not impossible, to use in modern terms.
Okay. Thank you for that particular video. I'm wondering, let's see, I'm just going to go to the chat questions right now because we have a couple here. From Doug, what type of emulsion was used for the glass plates and what is the expected archival life?
Well, I'll stick my hand up for that one at least a little bit. The emulsions varied enormously over the period that photographs were used, honestly. Some of the earliest photographs were actually what are known as wet process, and in fact, we're not looking at those. They were both difficult to take and not very sensitive. The modern ones, by modern I mean over the last roughly 100 years after the development of dry process, range, essentially they're all sort of silver-based emulsion in the sense of it's a gelatin type emulsion on some sort of substrate. We used glass because glass is dimensionally stable. The question is unfortunately very apropos for why we want to preserve these now, in the sense that emulsions don't last forever and have a variety of ways of failing, as I think we'll see a little bit later on. If Doug is interested, some of the names that were famous amongst the astronomical emulsion types were things like 3AO, 103AO. These essentially refer to the different prescriptions that generated the emulsion. The little a in all of these names, though, was for astronomical, which typically meant they were often more red-based than, more sensitive in the red than was often used for landscape photos or portrait photos around the time. The lifetime, I defer, I don't know. Some of them have lasted 100 years plus.
Well, we certainly have the ones. Oh, go ahead. Sorry, Lauren.
Yeah, a lot of that is going to depend on, how we preserve them going forward, the conditions that we store them in, the envelopes, the containers, the physical space that they're stored in. So right now, and you'll see this in a little bit, they're all in the basement, which is not an ideal storage place. But if you can get them into a repository that's, temperature and humidity controlled, I think you stand a better chance of preserving the longevity of that emulsion.
Yeah.
Another thing I can say is that a lot in terms of the longevity depends on how they were processed initially in the darkroom, particularly the cleaning and then the washing of them after the development was done. And if they were washed pretty well, then those chemicals were pretty much purged out of the emulsion. And once they were dry from there, it's pretty hard stuff, pretty resistant to degradation. But there we do have plates where the emulsion is like sloughing off the glass and where they left it in the wash too long. And, things
Very
didn't.
good.
But most of them are in pretty good shape.
Okay, good to know. Well, sometimes things like that happen and you have technical difficulties and lose your emulsion. And sometimes we have technical difficulties and lose half of our video. So that is where we were. We had a little bit of an issue with the video freezing, but my understanding is we have it back now. So we're going to try to just pick up the rest of that video and continue watching that. So we will once again try to finish this video on this part of the presentation, and we will see you again in a few minutes.
Hi, I'm Stephen Levine. I'm an astronomer here on the staff at Lowell Observatory, and I'm also the telescope scientist for the Lowell Discovery Telescope. So one of the appealing aspects for an astronomer coming to Lowell is that Lowell has a roughly 100-year collection of astronomical photographs of the sky, various objects, various portions, and a big piece, especially today, of astronomy, study of objects over extended periods of time. The digital age only really goes back to the late 1970s, 1980s, but if we can somehow make use of photographs taken as far back as the early 1900s, we can extend the time baseline that we can use to study objects by a good 60, 80, maybe even as much as 100 years. And one of the things we've learned is that we never know what we're going to find when we suddenly expand our study period, but also that the longer the period we have to study, we almost always find new phenomena in objects that we didn't expect. Variable stars show periods of variation that are almost always as essentially correlated with how long your study period is. If you studied for 10 years, you find 5-year variations. If you study for 40 years, suddenly you find these additional variations over periods of 20 or 30 years that you had no way to expect. And so I'm looking at this as not only are we interested in taking new data, but we have this gold mine sitting in our basement of data that are, until they are digitized, are difficult, if not impossible, to use in modern terms. The advent of the photograph actually was something of a quantum change in how astronomy was and could be done. Prior to that, what you had was some form of a written record or perhaps a hand-sketched record of what someone saw in the sky. There are lovely artistic examples of this, and from a Lowell perspective, we have all of the various drawings by Percival Lowell himself and the folks working with him of Mars, of various nebulae. But what that meant was that the only record you have was somebody's transcribed or perception of what they saw. The photograph provided one of the first means of providing an independent record of what you observed. So if I went out one night and I took a photograph, let us say, of Saturn, I could then say, well, I saw this and I saw that and it looked like this. But someone else could say, well, okay, can I see the photograph? And that was before that, there was no alternative. You could go back to their records or you could look at their sketches, but now you could say, can I see the picture? And that was if you think about it, that's a paradigm change in how the science is done, because suddenly there's a record that someone else can look at, someone else can evaluate independently. And that really started to come into play in the early 1900s, maybe up to sort of the 20s and 30s even. Plates or negatives, depending on what you want to call them, were astronomers' way of recording some portion of the sky on a particular date and time for future study. A number of projects, like I say, depend upon comparison of an observation from one date with an observation taken on another date. We look at the change of brightness of stars as a function of time. We look at the motion of stars, and people don't think about it much, but stars move. A premier program that covered the better part of probably 40 years of observatory history was what is now known as the Giggless Proper Motion Survey. This was a combination of plates taken between the 1930s, late 1920s, early 1930s, and as recently as the 1970s. And what astronomer Henry Giggless and his collaborators did was to first take what are known as first epoch plates, and in this case they were lucky. Clyde Tombaugh and his collaborators took most of those. And so they had those in the archives. These are large glass plates of the sky, and they tell you what the sky looked like in, say, 1935. And then Henry came back and in 1955 or 1960 took another plate of the same region of the sky and then compared the two. And what they were looking to see was what changed. And this is a common kind of astronomical project in the sense this was a large survey done in the only way it could have been done at the time, whereas now it would be done all digitally. And what Henry then would do, and all of the folks who worked with him, is literally take the plate from 1930 and the plate from 1960, put them side by side on a specialized machine known as a link comparator, and flip between one and the other. And they'd look at what it looked like here and what it looked like here. And what they would find, the high proper motion stars they were looking for, is that most of the stars in the background would look exactly the same between the two, except for one or two that would be here, and then would be here, and be here, here. And so as you blink back and forth, you would see it literally jump. And that was a type of survey project, and this is in fact exactly how Pluto was discovered. It's the same kind of blinking, looking for motion. And that's one kind of thing. This is, like I say, a project to look at the motion over time of objects in the sky. One is often faced with the question of, well, we could just retake the photographs. It's much faster, it's much more sensitive, they're much more uniform. What do we need the old plates for? But what you can't do is turn the clock back. You can't go back and take the sky in 1930. It was what it was, and the only records we have exist in the plate archives of observatories around the world. We have proposed in our starting a project to turn these roughly 30 to 50,000 glass plates and films into a digital archive of a sum of a history of the sky, covering whatever plates were taken for whatever research programs by astronomers at Lowell Observatory over the last 120 years. A big part of that program is a balance of material like this is falling apart. It's just aging. People who know how to handle photographs like this, glass plates are delicate. You have to handle them carefully. You have to know something about how to treat them. Make them difficult to use if you've never been trained in it. And furthermore, they only sit here. They're on campus. We wouldn't send them out. If you asked a shipper what they would charge for insurance for something like this, they wouldn't know where to start. The closest they can come is to go ask an art museum what would you insure a piece of art for, because they're irreplaceable. So anyone wanting to use these images of the sky has to come here right now. And then they have to demonstrate some ability to know how to handle these so that we're not worried about them breaking. But if we can digitize them, then as has been pointed out, anyone can get at them. The internet brings this to anyone in the world who has a network connection. There's no worry for risk. If Lowell vanishes off the face of the planet the day after we finish, these plates will still be preserved. One of the nice things about, or one of the potentially interesting things with digitizing plates like this collection is that, yes, we discovered Pluto out of it. Well, I should say Clyde Tombaugh discovered Pluto through this, but it's indicative of what could still be waiting in those plates. One of the early projects done after some plates from other observatories were digitized, for example, was when a new asteroid was discovered. Once the older plates had been digitized and the logs had been made public, and that second piece is critical too, people who had just discovered asteroids, for which you would have a very short arc on the sky, which means that your certainty of where it would be tomorrow is not good. They could predict it back to whenever those plates were taken, look on the plates, and in many cases find them. This is what has become the portmanteau precovery, meaning essentially to recover an asteroid from plates taken before where nobody noticed it because you weren't looking for it. And what it has meant is that in literally a few minutes, you could extend the arc of an orbit for an asteroid by 10 or 15 years, or 20 or 30 or 40 years, which meant that suddenly what was very uncertain became a very much more certain orbit, and meant that we could classify it much more quickly as being, we know where it is, we know what kind it is, and we know how to predict it. And similarly, there are, I am certain, a large number of observations of either known or yet to be discovered both asteroids and other moving bodies in the solar system on those plates that have never been measured.
Well, we had just been talking about Doug's question about the longevity of the emulsions on these plates, and to see that one plate with the flaking emulsion really brings home how fragile these can be. So that was a really vivid explanation of that particular question. We had a question as we were watching that video from Sophia, asking if there could be some other interesting things on the plates that haven't been noticed yet. And I think that after she had asked it, you had answered it in the video, Stephen, perhaps. But I'm wondering, you had mentioned that there may still be asteroids or solar system bodies on that plate or on other plates that have not been found yet. But I'm wondering, are there other types of discoveries that might still be made from the Pluto plate or from other plates?
I think the answer, and I would defer to Brian on this, but I think the answer is almost certainly absolutely yes. Not only do we look for things that move, say in the solar system, or stars outside the solar system over long baselines, but also there are things that change significantly in brightness. And one of the biggest things is, somebody discovers a supernova tomorrow. Well, one of the first things you want to do after tagging it is go back and find out what was there before it went off, so that you could correlate the explosion you're in the process of watching with something about its pre-explosion history, because this is in fact still a critical area in understanding stellar evolution, is not just when the explosion happens, but it's understanding what's the physics or what's the visible manifestation of the physics before the explosion, because that tells you something that might actually help you limit the kinds of answers as to what processes are going on in certain kinds of stars leading up to such a catastrophic event, just as one example. And historical plates like this tend to be actually invaluable for this kind of thing.
And so how, excuse me, how are you going to get the data from the plates to something that people can use?
The intent here is to use a commercial flatbed scanner with a transparency unit. So effectively, we're putting the plate down upon a piece of glass with a camera underneath and a light above, and you literally project the light through and you record the intensity of the light as it passes through the plate. You generate a digital image of it. This really was not viable with commercial scanners until a few years ago, just in the sense of reaching the point where the scanners have resolution similar to the actual grains in the emulsion on these plates. And we're lucky enough to have reference catalogs from other sources, in particular some of the mapping satellites like the Gaia project, that provide reference catalogs that allow us to actually calibrate the resultant images. And so we can match them up with other catalogs. And so plates from yesterday or 60 years ago can actually be matched against each other, and we can determine that this object is the same one as it is on that other plate, which is where the science really gets done. Yep,
got it. Okay. Do we, Brian, do we have is it possible that we'll be finding something like another Pluto in one of these older plates, or is that not a
I would say no exciting things in the outer solar system that we're going to find, and that's simply because the surveys that are going on now cover the sky very regularly every few days to much fainter limits, literally a factor of 100 almost fainter than the original Pluto camera plates went. And so nothing's getting missed that was picked up back then. And so there'll be other things, plenty of other stuff, but nothing, no new outer solar system objects.
Yeah. And of course, what we're looking for here is that brightness, size and brightness are correlated, right? If there's a larger body, it will tend to be brighter. Of course, it depends upon the albedo of the body. I'm going to use this opportunity to go back to an earlier question from Dulcimerist asking about the relative sizes of Pluto and the asteroid Ceres. And Pluto is about 1,500 kilometers across, I think. Did I get this right? And Ceres is about 900.
Yeah.
No, I think that's wrong. I think this must be in miles. I think I have my units
Yes,
confused.
Ceres is a little over 900 in diameter,
Right.
and Pluto's a little under 2,400.
2,400, yeah, thank you. So Pluto is significantly larger than Ceres, and therefore it's brighter as well as it shows up in these surveys. We have another question here from Doug, and I'm going to ask Lauren to address this one. Does the Smithsonian still have one of the Pluto discovery plates?
That's a great question. We were very excited last year when the Smithsonian contacted us and said that they were interested in returning one of the discovery plates that had been on loan to the Air and Space Museum since 1977. So they contacted me in November of 2020, said that they had it on display for a long time, but didn't feel like that was good for the long-term preservation of the plate. So they actually, as far as I remember, they made a replica from a scan. So both plates have been digitized, and then said, we would like to return the original plate to you. So we got it back in April of last year, and then we decided to have the grand unveiling on the anniversary of the New Horizons flyby in July. So a small group of us, including me and Brian and our historian Kevin Schindler, unpacked the crate where the plate was stored that had been shipped from Air and Space. And then we went over to the plate vault and somehow managed to avoid an insane monsoon downpour, got the other Pluto plate into the Putnam Collection Center with about 5 minutes to spare before the rain just started coming down, and we reunited the plates. So they're both back now at Lowell and safely stored in our collection center, which is really great.
Okay, excellent. Thank you. So what we're going to do now is go to our final video. And then once that is done, we'll come back and we'll chat some more with you. So we'll see you soon.
Hi, my name is Lauren Amundson. I'm the archivist and librarian at Lowell Observatory. We've got collections that have tiny little spectra plates that are 2 by 3 inches, all the way up to 14 by 17 plates that Clyde Tombaugh used in his search for Pluto. We have the 1905 search for Planet X, and that was kind of driven by Percival Lowell when he thought there was a planet out beyond Neptune, and so he instigated that search. We have the spectra plates that B.M. Slifer took, where he discovered the redshift expanding universe. We've got the Pluto search plates that Clyde Tombaugh took up that search in 1929. And then after that, Henry Gickless used those same plates to do what was called the proper motion survey. And that ran from about 1955 to 1975. And so there's a whole span of plates that were used for various research projects over the years. And it's a fantastic collection that's really kind of an untapped resource at this point because of the inaccessibility of, being able to pull plates out and look at them. So right now, basically all of our plates are down in a plate vault in the Slifer basement. They've been there for decades. And as we start to digitize them, part of that process is going to be moving them over to the Putnam Collection Center. That will entail cleaning them, scanning them, putting them in new sleeves or envelopes and new boxes, and then moving them over to the PCC where we have a climate-controlled repository. That'll be their final storage place. And so, yeah, there's, obviously risks inherent in glass plates. You have emulsion that peels off, you have breakage that can occur very easily. And so we really want to make sure that we preserve them physically, but then by digitizing them, that's sort of a means of preservation, but will also provide access for researchers. Right now, they're stored on wooden shelves, which is not ideal because wood outgasses, so metal shelves are actually the best storage for that. Most of them are stored vertically, which is the correct way, but if you go down in there, you'll see areas where they're stacked horizontally on top of one another, which is really bad. Some of them are just sitting in boxes that haven't even been opened yet. So it's going to be a big project for us to get them out of there, preserved properly, and then get them into the right storage in the collection center. It's been decades that they've been down there because there's never been another place for them to be located. And so, obviously a basement is also not an ideal place. You could have flooding. Harvard experienced that in their plate vault several years ago. They had a really bad flood. You could have insects, temperature swings, humidity swings. If there's a pipe that leaks or something like that, then you're in big trouble. So it's not an ideal place for them. The digitization process will make it easier for astronomers and researchers from all over the world to access our plate collection. The generation of astronomers that knew how to handle the plates is, significantly smaller than it used to be. So you're not going to get people that inherently just know how to safely handle the plates to come in and use them anymore. Having the plates available digitally will make them much more widely accessible than they are now. Actually, right now, they're virtually inaccessible, not only because of the fact that they're glass, which is inherently fragile. Obviously, you don't want people handling that, but because a lot of them aren't cataloged, and so people don't know what we have. As we start to digitize those plates, we will create catalogs that are available for everyone to look at, and so they'll know, they'll have the metadata side of it, what's there, what the object is, the date, the RA and DEC, all of that information, and then they'll be able to actually look at the plate as well and get the data that they need from that plate. The digital library of plates will be freely accessible to anybody in the world who wants to access them. We are using a flatbed scanner, and Stephen has set up a nice little area down in the plate vault, and when we get started on that, we'll use the scanner with some modifications to digitize the plates. And then we'll take photographs of the plate jackets with all the information on them. So that's an exciting project we're looking forward to getting started. Besides plates, we have documents. So we have the papers of our founder, Percival Lowell, of astronomers V.M. Slifer, Carl Lampland, E.C. Slifer. We have photographs, we have blueprints, drawings, audiovisual recordings, a lot of 3D artifacts. Very wide collection of materials. I'd say we've got about 1% of our entire collection digitized right now, which is actually fairly common for a repository because it's so hard. It takes a lot of time and money and effort to digitize. So we're slowly working our way through, kind of establishing what is priority, maybe based on, the condition that it's in, and trying to get that digitized, logbooks that might be fading, for instance, because they're written in pencil or diaries. That's the kind of stuff you want to get scanned first. And then other stuff that we just think is cool that we think people would like, we're digitizing that and putting it out there in exhibits and digital collections so people can view it. The plates on their own, they have a lot of data available, but a lot of them have notebooks or logbooks that go along with them. And so that'll tell the date that they were taken, what they were looking at, who the observer was. And those are very valuable. And so if you are digitizing one, you want to also digitize the other with it and then match those up. Same thing with a lot of, personal papers. You might have papers that are talking about a specific project, and then you can go to the glass plates that astronomer used and say, oh, this is the connection here between this. So, we really want to make sure that we digitize all aspects of that collection and make that available to everybody.
It's from the video. One of the things that I was really struck by is the potential from, once this collection gets to be digitized and all of the things that can be done with it, but at the same time, all of the work that it's going to take to get us to there. So we had a question in the chat earlier about who was going to have access, and I think that was covered, Lauren, in that particular one. So that was great. We have a question from Laurel. So how long do you estimate this digitization process will take?
3 to 7 years. And it's a wide range, but part of it just depends on, and there's no reason to move precipitously fast. So the key here is to do it slowly and pace ourselves and make sure we don't break anything.
Absolutely. And there's another question here from Sophia saying that noting that it's a huge undertaking, and are there such things as archive interns?
Yes, keep your eyes on the website for postings. That's probably the best way.
With such a big undertaking, it's going to need a lot of people helping out. Absolutely. So, for you, Lauren, are there? I mean, we've just been talking about all of the plates that are in the collection center or will be in the collection center, and then there's what kinds of extra information came with. So we have the plate jackets, and do we have the I think you mentioned logbooks as well, and what kind of information is in there?
Yeah, so when the astronomers, and Brian and Stephen can also speak to this, when they're out observing at the telescope, taking the plates, they would have a logbook to go along with it that would have all the relevant information. So who the observer is, the date, the object that they're looking at. And then that allows us to go back and say, match it up with the plate with all the other information that isn't captured on the plate itself on the glass. So it's very important that if you have those accompanying logbooks, that you digitize it all, keep it together, make sure that you have all of that accompanying metadata, because otherwise you lose a lot of the context of what's on the plate itself.
Have you found anything interesting in the logbooks, like little doodles or shopping lists or anything fun like that?
I wish I could say that I've looked at more of the logbooks, but I haven't. But I'm not sure if Brian or Stephen have seen anything while they're kind of perusing those.
I think there are, a fair number of interesting comments about the quality of the sky. Or I remember in we were talking about the emulsion, peeling off the glass, and there's a case where that's one of the Pluto camera plates that's in quite bad shape, and you look in the logbook, and it actually says Tombaugh wrote that we left it in the wash too long after the development process, because all the observatory staff decided to go down to Sedona and sit in Oak Creek on a Sunday afternoon or something, and they forgot to take the plate out of the water, and so it didn't do very well.
So we know it was a good day in the area then. Yeah, it's really interesting to think about, the personal lives that can be reflected in some of these scientific notes as well. Yeah, absolutely. We have a question from Cody. Lauren, how do you even start organizing and cataloging such a huge collection? And also, how many plates do you have in total in the archive?
I think we estimate 50,000 plates. In, I think, about 1991, Brian actually went through and created an inventory of the collections, which has been really helpful. We have it taped to the side of the shelf in the plate vault, which I love to look back at. But 2 years ago, I guess it was, right before the pandemic started and we shut down, I had hired an intern and she was going to start digitizing a very small subset of the plates just as kind of a pilot project. And when Lowell closed in March and she wasn't able to come in, we kind of had her switch gears. And so she came back in June of that year. And because she was working by herself in the basement, and Stephen and I weren't available to kind of assist with the scanning part of it, she did a large scale inventory of all the plates down there, worked with Brian, I believe, on that, and created the different collections, the different series, kind of did like an item level catalog of some of the plates. So we have a fairly good idea of what we have on a large scale. So that's actually, thankfully, not a huge concern. There are some of them that are going to be a little bit harder to probably identify and organize, but overall, I feel like we have a good grasp on that.
There's been there's a lot of commenting going on here about just the scale of this project. And so Delsmarist asks, how long does it take to digitize a single plate?
Some of it depends on the size of the plate, honestly. Basically, we're aiming for a fairly standardized resolution, something around 5 to 10 microns. And so if you have a 3 by 5 inch plate, that goes much more quickly than if you have, say, a 12 by 17 or 14 by 17 inch plate. The small scale plates still take the better part of 5 to 10 minutes. So a large scale plate is going to take something like 20 to 25. I actually haven't had the gumption to try a full 14 by 17 plate yet. We're not quite at that point in our testing.
Okay.
That's a part of why it takes so long.
Right, and then we multiply that by 50,000, and that's where we come up with the 3 to 7 years, or your estimate there. We have a question, I think probably for you, Stephen, from Andrea. How did you choose what digital scanner to use, noting that technology has really come a long way?
Andrea is absolutely correct. The technology has come a long way. Say 25 years ago, one would have done individual stars with small raster scans on what was known as a PDS system. Whereas now, the flatbed scanners, just on their own, would not be quite good enough. Like I say, there's the added benefit of having these high resolution, high precision catalogs of calibration stars that we can use actually to calibrate the scanner as well. The choice of the two scanners we're going to use was actually pretty simple, unfortunately. The larger one is, in fact, the only sort of somewhere between commercial and prosumer level scanner that's on the market at all, big enough to handle the large plates. And we got a second scanner in a more common size, slightly higher resolution, specifically so we don't have to run all the smaller plates through the big scanner, because the expectation is that it's a mechanical device with a bar that moves back and forth, and they have limited lifetimes. So.
Okay, thank you. We have a question here from Luis about how long can these be preserved, and I'm not sure if he's talking about the plates themselves or just the information. But I don't know. I'm thinking that maybe because we've talked a little bit about the glass plates, and then the emulsion is the thing that might not last forever, and they last different amounts of time depending upon how it was processed at the time. And we obviously have, plates that are more than 100 years old, maybe not here, but at other places. And then some that are, flake off pretty quickly. But I don't know if anybody wants to take up the more general question and think about, how long can we preserve these data for anybody who wants to come in the future to do something with it, to look for things.
Well, I'll take a stab at some of that anyway. One of the things, starting with the physical emulsions, some of them clearly we don't know how long they'll last because they still seem to be in pretty good shape. And I believe we do actually have plates in the collection over a century old at this point where they seem to be still stable and quite viable. The example, unfortunately, that was in some of the videos is a good demonstration of how some of the emulsions do fail. and what we fear most in some ways. Once the data are, a copy of the data are digital, in theory, as long as we keep the archive, as long as we keep up on the checksums and make sure that whatever storage medium the digital data are on could conceivably last indefinitely. And with the growth in computer ability, what it takes to make a new copy becomes easier and easier over time. So,
are there, Lauren? Are there protocols for preserving digital data?
Absolutely, and that's one of the things that we've been looking into for our other digital records, and I'm sure that will apply to these as well. But making sure that we preserve the integrity of those records moving forward, because right now a file that we can open with no problem, 5-10 years from now, we have no idea if that will be accessible. And so that's a really big challenge that archivists face, is that we like to say that digitization is not a preservation technique, because you're not guaranteeing that those digital files will last any more than the originals. So it's very important that you not only work to ensure the integrity of those digital files, but you also save the original physical objects as well, so that you've kind of got that backup. And so that'll be an additional challenge to this project, is making sure that we do all the things we're supposed to ensure that those digital records last a very long time.
Thank you. Yeah, it's interesting things to think about. We're coming up to the end of our program here, but I wanted to just end by asking you if there's, what do you hope we find, what we discover when these data are digitized and taken a look at? Does anybody have any hopes that of cool things that we find?
I can give some examples. One that I often cite is Stephen mentioned the supernovae, and one of the things that happens with supernovae in now, I guess you would say, in the current time, is that radio telescope data can allow you to identify remnants from the supernova, the gas expanding out from the supernova, and that often doesn't appear for something like 100 years after the actual explosion happens that you'd see. But having an archive like this that goes back 100 years allows you to say, well, it was on November 27th, 1930 that supernova actually erupted. So you actually know when it happened, rather than saying, well, there's a supernova remnant here, but we don't actually have any idea, other than being young, quote unquote. We don't really know any more about it. But with an archive like this that goes back a long way, you can actually identify such objects. And that's, an example.
Yeah. Does anybody else have any other?
I actually would follow that one up with a reference to last night's talk by Tom Palakis on time-lapse stuff, because he had a very nice example of watching the expansion of the Crab Nebula from photos starting back in 1909 that had been essentially aligned and then overlaid with more modern ones. And not only can you see, for example, as Brian's pointed out, when something started, but from some of those, you actually can get a direct quantitative measure of how they expand, which actually tells you an immense amount about what the medium is that it's expanding into. What's the interstellar matter around that star, for example, like what's the density, how fast is this shock wave expanding? And so this is the kind of thing that at the moment, we only have enough of a baseline to really do off of photos combined with modern data. And actually, that's what I guess I'm most looking forward to, is the combination of the oldest with the newest.
Yeah. And in fact, the expansion of the Crab Nebula was actually discovered by Lapland on his old plates with the old 42-inch telescope.
Oh, I didn't know that.
Yeah.
Oh, that's neat.
People say, like, oh yeah, it wasn't discovered by Space Telescope. It was discovered a long time ago here.
Right. And just to give context here, the Crab Nebula is a supernova remnant. It's a really beautiful.
Erupted in 1054 AD.
Yeah. Lauren, did you have anything to add?
No, I'll just assist with the process.
Oh, we really appreciate that.
It's an essential part of it.
I was going to say
Yes.
she's underselling herself. Yeah,
Yeah.
she is critical to this.
Absolutely. Absolutely. Well, it's just a fascinating discussion and great videos. And I thank everybody for putting, for all of your work in putting these together and for joining us tonight. And so since we're now 5 minutes past the hour, we're going to end here. So thank you all and good night.